Vision is the most dominant sense for people with sight. This allows us to see the beauty of the physical world. However, a human eye has a limited capability to see things beyond its capacity to see. Thus, optical devices help aid one's vision in order to see things clearly. Before we proceed to our formal discussion on curved mirrors and lenses, let us revisit some of the most essential concepts that we have learned from the previous weeks. We have learned that light is a type of electromagnetic wave which lies just above the frequency of the infrared rays and below the frequency of ultraviolet rays. We also learned that among all electromagnetic waves, light is the only one that can be perceived by naked eyes. We also learned that light exhibits reflection on opaque objects such as mirrors and refraction on transparent and translucent materials. We also learned in our previous lesson that the characteristic of images formed by plane mirrors are as follows: same size with the object, vertically upright but laterally inverted, the image is located at the back of the mirror, and the image is virtual in nature. We already know the properties of image formed by plane mirrors. A plane mirror is a mirror whose reflecting surface is flat. What about this mirror? Is this also a plane mirror? This is a mirror as it has a smooth reflecting surface. But this is not a plane mirror because its reflecting surface is not flat. This reflecting surface is curved. Hence, it is called as a curved mirror. What about this one? This is also a curved mirror. The only difference between the two is that the reflecting surface of this mirror is curved inwards, while the reflecting surface of this mirror is curved outwards. Can you think of other materials that have curved mirrors? A shiny surface of a spoon is an example of a curved mirror. The spoon has two reflecting surfaces, one curved inside and the other one curved outside. Now, the specific type of mirrors that we are interested in is called spherical mirrors. In fact, these mirrors are spherical, but they do not look like one. Why are they called spherical mirrors? They are called spherical mirrors because their reflecting surface is part of a sphere. Both are given special names. Curved mirrors that have a reflecting surface curved inwards is called a concave mirror. And the other one that has a reflecting surface which is curved outwards is called a convex mirror. Inwards concave, outwards convex. We are now going to identify the properties of images formed by spherical mirrors. But before that, we need to know some important terms that are related to spherical mirrors. We have our concave mirror on the left and convex mirror on the right. When we say concave, it's inwards and convex outwards. The center of the reflecting surface of the mirror is called the pole. We already know that the reflecting surface of one of the mirror has one section of the sphere. The center of the sphere is known as the center of curvature, and the radius of the sphere is known as the radius of curvature. Join the pole and the center of curvature with a line. This line is known as the principal axis. The midpoint between the center of curvature and the pole of the mirror is called the focal point. The radius of the curvature of the mirror, if you are going to look at the video, the radius of the curvature of the mirror is always greater than the aperture of the mirror. Aperture is a part of the mirror which is exposed to light. The aperture of the mirror is where light is incident on the mirror. If we are going to hide some part of the mirror, then we decrease the aperture of the mirror. These are the different terms that we need to learn when studying spherical mirrors. The ray diagram. This is an example of a ray diagram. A ray diagram shows the path that light takes in order to make an image. In this kind of ray diagram, we are making use of a concave mirror because its reflecting surface is curved inwards. Concave mirrors are also known as converging mirrors because real light rays tend to intersect at a specific point in order to create an image. In a ray diagram, you can see three rays that intersect at a certain point. An image is formed as three rays intersect. The tip of the image or the arrowhead should be drawn at the intersection point of the three rays, and the bottom part of the image towards the principal axis. Let us now proceed to the step-by-step procedure on how to write each ray in the ray diagram. So let's start with ray number 1. Ray number 1 is drawn from the tip of the object parallel to the principal axis towards the aperture of the mirror, and is reflected on the focal point of the mirror. That is how you are going to write ray number 1. For ray number 2 is drawn from the tip of the object, passing through the focal point towards the mirror, and reflected parallel to the principal axis of the mirror. That is for ray number 2. Ray number 3 is only for checking purposes, whether or not rays 1 and 2 meet at a specific point, and that specific point is the correct location. For ray number 3, we need to draw the line coming from the tip of the object, passing through the center of curvature to the mirror, and reflected back on the center of the curvature. The intersection of the three rays is the location of the image. Ray diagrams for concave mirrors. We already know that concave mirrors are mirrors in which the reflecting surface is curved inwards. In the following ray diagrams, we are going to use concave mirrors. Concave mirrors can create wide range of characteristics of images, and we termed it as the salt of the image, where S stands for the size of the image, A stands for the appearance, L for location, and T for type. For the size of the image formed by concave mirrors, it may range from smaller to same size to bigger than the actual size of the object. For the appearance, it may appear inverted or upright. The location of the image formed by concave mirrors may be placed beyond C or beyond the center of the curvature, at the center of the curvature, between the center of the curvature and the focal point, or it may also be located at the back of the mirror. For the type of the image formed, it may range from real to virtual. Always remember that all real images are inverted, while virtual images are all upright. Let us start by this ray diagram. We are making use of a concave mirror still, and the location of the object is beyond the center of the curvature. The object is represented by the arrow, which is found beyond the center of the curvature. So let's start drawing ray 1. Ray 1 comes from the tip of the object, going parallel to the principal axis to the mirror. And it will be reflected on the focal point of the mirror. Next, for ray number 2, it comes from the tip of the object, passing through the focal point of the mirror and being reflected parallel to the principal axis. If you have noticed, the two rays intersect at a specific point, or the reflected rays of the two rays are intersecting at a specific point. This is where the image would be formed. Please make sure to write the tip of the image on the intersection of the two rays and extend the line going to the principal axis. So that is how you're going to draw the image. For the result of the image, if you have noticed, the size of the image is smaller than the actual size of the object. And the image formed is inverted. For the location, the image is found between the center of the curvature and the focal point, while the type of image formed by it is real, since real light rays tend to converge at a specific point, and since the appearance of the image is inverted. For this case, the location of the object is found at the center of the curvature. So let us try to determine the result of the image in this case. Let's start with ray number 1. Ray number 1 still comes from the tip of the object, parallel to the principal axis to the mirror, and passes through the focal point of the mirror. Ray number 2, from the tip of the object to the focal point, to the mirror, and parallel to the principal axis. So where is now the intersection of the two rays? The intersection of the two rays is found here. Therefore, this is where the image will be formed. The result of the image are therefore same size as of the object. It is inverted, located at the center of the curvature, and the type is real. For this case, where the location of the object is found between the center of the curvature and the focal point of the mirror, we'll draw ray number 1, and of course ray number 2. And if you have noticed, the intersection is found here, and therefore the image is formed here. So the result of the image, the size of the image is larger than the actual size of the object. The appearance is still inverted. The location is beyond the center of the curvature, and the type of image is real. For this case, we are placing the object at the focus. So let's draw ray 1. Ray 2 is coming from the tip of the object to the focal point. Okay, if you have noticed, there is no intersection that happens of the two reflecting rays for ray 1 and 2. Therefore, there is no image formed if the object is found at the focal point of the mirror, or it may be that the image is at infinity, or it is formed at a very far location. For this case, the location of the object is found between the focal point and the vertex of the mirror. When we say vertex, it is the intersection of the aperture of the mirror and the principal axis. So that the vertex of the mirror is located here. Now, let's draw the first ray. The first ray comes from the tip of the object, parallel to the principal axis, and going to the focal point. The second ray supposedly comes from the tip of the object going to the focal point. However, since the focal point is found at the back portion of the object, therefore, it is incident, or it should be incident on the mirror relative to the location where the focus is found. So the angle should be the same here. So it will be reflected here. And then, okay, this ray will be reflected parallel to the principal axis. And we need to extend the reflected rays because at the back of the mirror, the reflected rays, which are represented by the broken lines, or apparently the reflected rays or extension of the reflected rays, are intersecting at the back of the mirror. And this is where the image would be formed. So what is now the result of the image formed by a concave mirror if the location of the object is between the focal point and the vertex? The size is larger than the actual size of the object. The appearance is upright, meaning to say the top and the bottom of the object is the same with the top and the bottom of the image. And the location of the image is found behind the mirror. The type of image, therefore, is virtual, since the appearance of the image is upright. And we can say also that it is virtual since the rays that are intersecting are not real light rays. Therefore, they are virtual, or the image that is formed is virtual. In this case, the location of the object is found at the infinity, where it is far from the mirror, very far from the mirror. If you have noticed here, the object, which is represented by the candle, is being moved farther from the mirror. And since the screen has a very limited size and we cannot further move the mirror, so we will just have to do some estimation. We will now use the different rays. Okay, so if we further move the object from the mirror, then if you have noticed, the result of the image that will appear are as follows. The size of the image formed would be very, very small. It's almost like a dot if we move the object further from the mirror. The appearance would be inverted still. The location is nearing the focal point of the mirror or at the focal point of the mirror. And the type of the image formed is real since it is inverted. Ray diagrams for convex mirrors. In this ray diagram, we are making use of a convex mirror. If you have noticed, real light rays tend to diverge from the mirror. However, the reflected rays are being extended at the back of the mirror, in which the intersection would be located. And therefore, convex mirrors are said to be diverging mirrors, since real light rays tend to diverge from the mirror. In order to make the ray diagram for convex mirror, let us start by drawing ray number 1. Ray number 1 comes from the tip of the object, parallel to the principal axis towards the mirror, and is reflected relative to the location of F at the back of the mirror. This ray will be extended at the back in order to see whether it hits the focal point, and it is being symbolized by the broken lines. Ray number 2 comes from the tip of the object to the mirror relative to the location of the focus at the back of the mirror, and is reflected parallel to the principal axis of the mirror. The reflected ray in this case will be extended at the back part. because this is where the image will be located. Ray number 3 is for checking purposes whether the two rays tend to diverge at a correct point behind the mirror. So for ray number 3, it is drawn from the tip of the object to the mirror relative to the location of the center of the curvature. And this will be reflected back on the same path. We extend this ray going to the back of the mirror relative to the location of the center of the curvature. So that is for ray 3. Let us now try to complete the ray diagram for convex mirror. So for convex mirror, it does not matter where the object is being placed, for as long as it is in front of the mirror. At any point in front of the mirror in the principal axis, the type or the characteristics of the images formed by it will just be the same. So let's start by drawing the first ray. First ray comes from the tip of the object going to the mirror parallel to the principal axis, and it will be reflected relative to the location of the focal point at the back. And we extend this light rays to the focal point at the back of the mirror. For ray number 2, from the tip of the object relative to the position of the focal point, and since this is a mirror, so it will be reflected parallel to the principal axis. The reflected ray will be extended further at the back portion of the mirror where the intersection will be created. And the intersection is where the image will be formed. So what is now the result of the image formed by convex mirrors? The image formed by convex mirrors are smaller in size compared to the size of the object. They are also upright. The location is behind the mirror, and therefore it is virtual. It is considered virtual aside from the fact that it is upright. It is also virtual because not real light rays are intersecting at a specific point. These are just apparent light rays coming from the reflected rays of this diagram. Lenses. How do you form lenses? We arrange two prisms so that the rectangular surface face each other. The parallel rays incident on the prism are merged on the other side after refraction and intersect on a certain point. Let us insert a few more slabs of rectangular prisms between the two prisms. The parallel rays incident on such an assembly will undergo maximum refraction at its top and bottom. The rays undergo no refraction on the center of the lens. If we arrange two more prisms at the side of this arrangement, the incident rays passing through them also converge at the same point. A single piece of glass formed in this fashion is called a convex lens. A convex lens is an equally curved surface of two spheres. The center of these spheres are called the center of curvature. The radius of the sphere is called the radius of the curvature. The line that joins the two centers of both of the spheres is called the principal axis, which passes through the optical center of the lens. The light rays that are parallel to the principal axis and incident on one side of the lens undergo refraction and converge on the point on the principal axis on one side of the lens. This point is called the focal point of the focus. The distance between the focal point and the center of the lens is called the focal length. The focal length of a lens depends on its curvature. Take two lenses of the same diameter but of different thickness. When parallel light rays are incident on them, you can observe that the light that passes through the thick lens undergo more refraction and converge at a short distance, as compared to a thinner lens which causes less refraction, Thick lens has a shorter focal length than the thin lens. The image formed by a convex lens in this case is a real image of an object. The convex lens can focus the light from the sun to a point on the other side of lens. The concentration of light energy at this point causes the paper to burn. The lens of our eyes is convex in nature. We should not look at the sun directly because it can damage our eyes permanently. So we already know that light rays incident on a convex lens tend to converge on the other side, therefore considered as a converging lens. Look at another kind of lens, which diverge light as rays pass through it. These are called concave lenses. Arrange two prisms with their vertices in contact with each other and place two rectangular prisms on the side of each one. Light rays incident on this kind of lens tend to refract away from the center. These cause divergence of light rays. A single piece of glass designed in this fashion is known as a concave lens. When parallel rays are incident on a concave lens, they tend to refract and diverge as they pass through it. If we extend the refracted rays backwards, they meet at a certain point in the principal axis on the side where the object is being placed. This point is called the focal point. The sun viewed from a concave lens would appear as a point. If you place a paper at this point, it will not be heated. The image formed in this case is a virtual image. The concave lens are used to correct short-sightedness, or also known as myopia. The concave lens are used also in the peepholes to get a diminished size of a person outside the door. Ray diagrams for convex lens. This is an example of a ray diagram that makes use of a convex lens. And we know that convex lenses are also known as converging lens, since real light rays tend to intersect at a specific point in the ray diagram. Take note that in this ray diagram, we are making use of two sets of focus and center of curvature. Please also take note that 2F is just equivalent to the center of the curvature. The left side of the lens is called the prime side because F here is prime and 2F is also prime. On the right side, we have our focal point, which is F, and the center of curvature, which is symbolized as 2F. In order to create the ray diagram for convex lens, we need to start by drawing the first ray. Ray 1 starts from the tip of the object parallel to the principal axis to the center of the lens and is bent towards the focus. Ray number 2 comes from the tip of the object passing through the F prime to the center of the lens and bends parallel to the principal axis. Ray number 3 is still for checking purposes. We may or may not include ray number 3 in the ray diagram. So for ray number 3, that comes from the tip of the object passing through the vertex of the lens. Let us now consider the objects placed at different locations in front of a convex lens. If the location of the object is beyond 2F prime, what will be the result of its image? So let us draw the first ray. The first ray comes from the tip of the object to the center of the lens towards the focal point of the lens. Ray number 2 is coming from the tip of the object to F prime to the center of the lens and bent parallel to the principal axis. And for ray number 3, in this case, we are going to write ray number 3 or draw ray number 3 that comes from the tip of the object to the center of the lens, or to the vertex of the lens and the principal axis. And if you have noticed, all three rays intersect at a specific point where the image will be formed. The image formed in this case, if the object is beyond 2f prime in front of a convex lens, are as follows. It is smaller than the actual size of the object. It is inverted. The location is between f and 2f, and the type is real. If the object is located at 2f, what will be the result of its image? Let us draw the first ray, the second ray, and of course the third ray. If you have noticed, the intersection is formed at this point where the image is being formed. The result of the image are as follows. Same size as of the object, inverted. It is located at 2f, and it is real. How about if the object is placed between 2f prime and f prime? Let us draw ray number 1, ray number 2, and of course ray number 3. If you have noticed, the intersection is found at this part. Therefore, the result of the image are as follows. Larger compared to the size of the object. Appearance is inverted. The image is located beyond 2f, and the type is real. If the location of the object is found at f prime, so let's draw ray number 1, ray number 2, and ray number 3. If you have noticed, there is no intersection of the three rays, therefore, there is no image formed if the location of the object is at f prime, or we can consider that the image is at infinity. If the location of the object is between f prime and v, what would be the result of the image? The result of the image will be as follows. So this is our object, which is our candle, and our image is here. So the size of the object, the size of the image is larger compared to the size of the object. The appearance is upright, and the location of the image formed by the convex lens in this case is between 2f prime and f prime. And the type of image formed is virtual. How about if the object is found at the infinity or very far from the lens? Let us consider this simulation. So if we try to move the object farther from the lens, then let's try to draw the rays. So if you have noticed, the result of the image formed by it are as follows. Okay, the image may be very small. It is very small, like it's a dot. It's almost like a dot. And then for the appearance, it is still inverted. The location is nearing f or at f if the object is very far from the lens. And the type is real. Ray diagram for concave lens. This is an example of a ray diagram that makes use of a concave lens. A concave lens is considered as a diverging lens. If you have noticed, real light rays tend to diverge as they pass through the concave lens. In order to draw the ray diagram for concave lens, let us try to draw first ray number 1. Ray number 1 comes from the tip of the object parallel to the principal axis to the center of the lens and bends outwards relative to the location of F prime. In this case, we are going to extend the refracted ray backwards going to F prime. For ray number 2, it comes from the tip of the object to the center of the lens relative to the location of F and bending parallel to the principal axis. And we need to extend the refracted ray backwards. That is for ray number 2. Ray number 3, from the tip of the object passing through the vertex of the lens. Again, this is just for validation purposes, whether or not rays number 1 and 2 are on the correct position where they intersect. Let us now consider the ray diagramming for concave lens. The location of the object is beyond 2F in this case. However, even if we move the object at different points in front of a concave lens, it will form the same set of characteristics. So let us draw ray number 1. From the tip of the object going to the center of the lens parallel to the principal axis, and it will be bent outwards, and the bending is relative to the location of F prime. And for ray number 2, coming from the tip of the object to the center of the lens relative to the location of F on the other side. And then it will be refracted parallel to the principal axis, and the refracted ray should be extended at the back. For ray number 3, it is just simple, from the tip of the object to the vertex of the lens. So the intersection of the 3 lines is here. This is where the image will be formed. Therefore, the result of the image will be as follows. The size is smaller compared to the actual size of the object. The appearance is upright. The location, it is found between F prime or V, or within the prime side of the lens. And the type is virtual. Application of spherical mirrors and lenses. Uses of concave mirrors. A concave mirror has a capability to create images that are larger or smaller in size, and virtual or upright, depending on the position of the object. Thus, there are many uses of concave mirror. In torch lights or headlights, a parallel beam of light is obtained by keeping the source of light at the focus. In floodlight, in order to get intense beam of light, the source of light is placed just beyond the center of the curvature. Reflecting mirrors for projector lamps. In this case, the object is placed at the center of the curvature to obtain the image of same size. To collect heat radiation in solar devices, the panel to be heated is kept at the focus of the concave mirror, which focuses the radiation from the sun to the panel. Shaving mirrors, dentist's mirrors, produces an upright, virtual image and of highly magnified image of the object, placed between the focus and the pole of the mirror. Solar furnaces. Large concave mirrors are used to concentrate sunlight and produce heat in the solar furnace, which is at the focal point. Uses of convex lens. Simple microscope uses a single convex lens of small focal length can be used as a simple microscope. Magnification of simple microscope is about 20 times. It is being used by watch repairers and jewelers and etc. Compound microscope is a combination of two convex lenses having short focal lengths and are used in compound. These are used in the compound microscopes. It is used in labs to observe cells, microorganisms, bacteria, and etc. Telescope. It is a combination of two convex lenses, and it is used in astronomical telescopes. The uses of astronomical telescopes is to get detailed pictures of planets, astronomical bodies, and etc. Optical instruments, convex lenses are used by cameras, projectors, spectrometers, and etc. Spectacles uses convex lens in order to correct defects like hyperopia. Hyperopia, or also known as farsightedness. Vision is the most dominant sense in most people with sight. The organ of sight is the eye. Think of it as a slightly irregular hollow sphere that takes in light and translates it into images. If we enlarge the eye and look inside it, we can discover how it's done. Inside the eye are various structures working together to create an image, which the brain can understand. Among these is the cornea, a clear dome-like structure covering the iris, which is the colored part of the eye, the lens directly below it, and the retina, which lines the back of the eye. The retina consists of thin layers of light-sensitive tissues. This candle helps us understand how the eye captures images and sends it to the brain. The candle light passes through the cornea, as thus it bends and refracted on the lens. As the light passes through the lens, it is bent the second time. And finally, it arrives at the retina, where the image is being formed. This double bending has reversed the image and turned it upside down. Fortunately, the image will be reversed right side up in the brain. The image needs to travel in the form of an impulse along the optic nerve and travels on the occipital lobe of the brain. Let us now discuss two of the most common conditions that causes blurry vision. The eye shape is important to keep light in focus. In a normal vision, light is focused precisely on the retina of the eye, where the focal point is located. What happens when the eye is longer than normal? The longer the eye, the more distance there is between the lens and the retina. But the cornea and lens bends the light on the same length. That means the focal point is somewhere in front of the retina and not on the retina. This makes it difficult to see things far away. A person in this case is considered a nearsighted person or person with myopia. In order to correct this vision, we need to use a concave lens. The lens widens the light and passes through the cornea and lens that pushes the focal point backwards and on the retina. Farsightedness is the opposite of nearsightedness. The eye's length is too short and the focal point in this case is found behind the retina, making people with farsightedness difficult to see things up close. This condition is called hyperopia. A convex lens can correct this condition by narrowing the light rays that passes through the cornea and the lens, making the focal point move to the retina of the eyes.